Okay, hello class. Next video, next topic is back to our south of the border, our road trip story. We're all on the bus driving from Charleston to Raleigh, and south of the border, there's a police officer with a radar gun, and he can get our instantaneous speed. And we want to see if there's a way to calculate instantaneous speeds. And we know that has something to do with tangent lines. So I'll put in our red tangent line here. I'll just sketch it. That's the thing we want to get the slope of, but we just don't know how to do it right now because we have our slope definition always involves 2 points on the curve. And here's our f of x. And oh, notice that I added a function. I gave you an explicit algebraic representation rather than just drawing a picture this time. This is a function that actually fits that shape. It's got that sort of parabolic increase here, and it does go through these points 0, 0 to 120. For 280, and it's given by this, 5x squared plus 50x. Again, you can look at that right away and notice that it's nonlinear because it's not y equals mx plus b. It's got this squaring variable immediately tells you it's nonlinear, which again fits the shape of the curve, which we knew was nonlinear. Okay, so after all that review, again, our goal is to get the slope of this red line, but the slope formula involves change in y over change in x. And we showed that we could get the slopes of certain secant lines last time. We knew that the slope of this secant line right here from 2 to 4, when x was 2 to x equals 4, this is a secant line because it touches the function twice. We can easily get the slope of that line by change in y minus divided by change in x. And we said last time that this one had a slope of 80 miles per hour because it's change in y over change in x. Not the one we want though. We want the slope of this red line. We know the slope of the red line pictorially has to be what? Is it greater than 80, less than 80, quite a bit less than 80? We can definitely say it's less than 80, right? And our graph isn't to scale, so it's hard to do more than that. But we can say it's positive and it's less than 80 at this point. But what we're going to do is this idea of we're going to do a limiting process of taking a bunch of secant lines, which again, not what we want, but maybe they'll help us get closer to what we want. And so suppose instead now between 2 and 4, we go between 2 and 3. Well, now we're up here on the function. This would be the point on the function. Maybe I should put that in another color because there's so many blue in here, I'm confusing myself already. Here's our function in black. A thick black line is f of x. All right, this time we're stopping at 3, going from 2 to 3, and we'll see if we can get, at that point of tangency, the secant line between 2 and 3, easy to draw. I have 2 points on the curve, I just connect them with a line. And so here's another, in blue, another secant line, right? Again, not what we want, but you can see from the picture that this secant line between 2 and 3 looks much closer to the tangent line than the secant line above from 2 to 4, right? So we're getting a little bit closer. Now if we can get the slope of that secant line between 2 and 3, which we can, so we just need to know what is the point. When x equals 3, what is y? How do you get that? So again, I give you an x and you want a y, what do? You apply the function rule. For any x, you apply it to the function rule. So really it's just saying, hey, go spend some time and get f of 3. Function evaluation. F of 3 says wherever I see an x, I stick a 3. So I'll have 3 squared is 9 times 5 is 45, plus 3 times 50, 150, to 195. So that means after 3 hours, you've traveled 195 miles. We're all on the bus together. We've gone 195 miles from Charleston in 3 hours. So now that I have 2 points, and I'm connecting them with the secant line, I can get the slope of that secant line by doing change in y, which is what, 75 divided by 1 is 75. So the slope of this line is 75. And now we know that's closer, that's a much better approximation to the slope of the red tangent line that we want. So we can say at this point, the slope of the tangent line, it's a positive number and it's less than 75. And hopefully at this point you see where we're going with this, that we're just gonna keep on doing this one iteration at a time. An iteration is a thing that you do repeatedly. We did it once, we did it twice, we're gonna do it a third time. And maybe we'll go between 2 and 2.5. We'll just keep shrinking the distance and getting closer to south of the border. Because again, secant lines have to have some duration. And if we can just make the duration shorter and shorter each time, then maybe our secant line will get closer, well, it definitely will get closer and closer to our tangent line. And that'll happen for any function, no matter how crazy nonlinear, as long as it's a continuous function. As you shrink the distance between your points of sequency, you keep shrinking that, your secant lines are going to converge to your tangent line. So let's see it pictorial. Let's put one more in there. Otherwise, the graph is probably going to get a little too cluttered too soon. All right, so maybe between 2.5 and 2. That's our duration, just a half an hour this time. We'll go to the function, draw a point of tangency. This will be 2.5, and that's a harder evaluation to do in our heads. Let me see, I think I did this in our book. Yeah, we're gonna have that the slope of this secant line, so this is f of 2.5. You can pause the video and evaluate that yourself, but the slope of this secant line here is going to be 73. Again, that line, the blue secant lines are converging, getting closer and closer to the red tangent line, which is the one we want. We're really good at getting slopes of secant lines, no problem. It might be tedious to do some function evaluations to get these points and do the change in y or change in x, and that might have some decimals and fractions in there, but doable, no problem, right? It's straightforward to do that. And so let's make a few generalizations at this point. So as h, we're going to call h the distance between the points of tangency. So h started off that big, and then h went to this big, and then finally this big. As h, the distance between the two points, sorry, I said tangent, I meant sequency. Sequency. Approaches 0. What happens? So as h, the distance between the 2 points that you're looking at, we started with here and here first, and then we shrunk that a little bit to here and here, and then we shrunk it again to here and here, and we could keep shrinking and shrinking and shrinking until the 2 points are just right next to each other, right? Started here, 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 here. Tiny, tiny, tiny. And we can do that, make them infinitely close together, right? And then, but we can still get their slopes, the slopes of the secant lines. As that happens, what can you say about the secant lines? The secant lines have to do what? They have to approach the tangent line. Again, we see that visually with this function. Try any other function you want to draw. There's a couple more examples in your book. I ask you to flip and animate the book, flip the pages, the edges of the page in your book like this, and make a little flip book, and you'll see for a particular function called the fingerprint function that works. But draw a couple more over here and pick any 2 points on there. Pick the tangent line that you want to get. Keep shrinking the h and see what happens. And it always, always happens that your secant lines converge to your tangent line. So what does that mean about the slopes of the secant lines and the slope of the tangent line, which is what we're really interested in, right? The slope of the secant lines has to converge to the slope of the tangent line. Has to happen. As h, the distance between those 2 points shrinks, the secant lines converge to the tangent lines. Those blue lines get closer and closer to the red line. Therefore, the slope of the blue lines has to converge to what we want, the desired slope of the tangent line, right? This was the big deal for us. That's what we were trying to get. We just didn't know how to do it because our formula always needed 2 points. Well, here's the magic. This is the neat thing that Newton and Leibniz, the co-inventors of calculus, said. I don't know how to get the slope of the tangent line, but I'm really good at getting the slopes of secant lines. So let me just take what I know and do it in a limiting process, converge, iterate and iterate and iterate until I converge to the slope of the tangent line. This unknown value they were able to get by working on something they were good at doing. And They did an approximation that they repeatedly refined. We're going to see that over and over in calculus. Approximate, refine, limit, that three-step process. Okay, and there's a table in your journal's radar gun mystery page. There's a table here that shows H is shrinking, and I made it really tiny. It started off at 2, like we did here. From 2 to 4, the distance was 2, and then the distance from 2 to 3 was 1. So those are the first 2 rows in this table. First couple rows. And then I shrunk it so tiny, I said the distance between the points was 0.01. It was 2, and make some space in here. It was really tiny, right? At 2, and then right next to it, 2.01, right? So I did the distance between 2 and 2.01. H was 0.01. And then I did H even tinier and tinier and tinier. And when that happened, what we saw in this table was that the slope of the tangent line, the slope of the secant lines converged to 70. Like the secant lines went to something like this. They kept getting closer and closer to 70. Right? They started coming down from like 70.5. So if you had to then read that table, you would conclude that the slope of the tangent line that we're interested in, you start seeing the pattern, right? The smaller H gets, the closer the secant lines are getting closer to 70. And it turns out that this is true. The slope of the tangent line is exactly 70. 70 miles per hour was our instantaneous radar gun speed when we passed south of the border. At that moment, at one instant, not over duration, at that one instant, we had an exact speed of 70 miles per hour. All right, so key points here, but now we actually have to go ahead and try to do some calculation to figure this out. And that's gonna be through something called the limit definition of the derivative. So I'm gonna introduce that next. We're going to see this formula a lot. And it ties together several ideas that we're going to have. We're going to call f prime of x as something called the derivative. We're going to deal with that a lot in chapter 2. Maybe if you've had a calculus class or just even a pre-calculus, you might have seen this word before, the derivative. If I have a function f, I can create another function related to that that is derived from it. And that's how I got the name derivative. And we put prime there for the derivative function. And it turns out that this represents the slope of a tangent line at a point of tangency x, which we also know is equivalent to saying this is an instantaneous rate of change at the point x. Instantaneous change has to be at a particular point. And now we have to explain this definition. We have to understand it. I'm not going to make you calculate derivatives with this because we're going to, when we get to chapter 2, have a shortcut way of calculating derivatives. That is a much easier definition, a much easier way to calculate derivatives. But this one is key to understanding why we're doing this, what a derivative is, and how they came up with these shortcut rules, and the meaning of a derivative. It helps us remember that and keep that in mind all the time. Okay, so this is going to be somehow related to what we had over here, that secant lines are going to converge to tangent lines. And so I'm going to draw a picture that explains this formula. But the first thing about the formula to notice is we have a numerator and a denominator. And in the numerator, we have f values. Remember, f of x's are y values. Those are heights. And in the denominator, we have some x things. X values go this way, right? Our x-axis. And so y values in the top, x values in the bottom. So that already looks like slopes, right? That should key you off that change in y's, change in x's, right? We have the minus signs here. The second thing to notice about this formula is that the denominator has an x plus h minus an x. Just using our algebra, we know we don't really need all those x's, we can just call that h. And this is probably, again, if you've had a calculus class, you probably have seen this before and remember it. This is the familiar, most common definition, the limit definition of derivative, f of x plus h minus f of x all over h. And then we're going to talk about this limit in a bit. But the limit as h goes to 0 is exactly what we were talking about here. As h, the distance between the 2 points of secant c approaches 0, the secant lines approach the tangent line, therefore the slopes of the secant lines approach the slope of the tangent line. And that's what's actually represented in this formula. Let me draw a picture that goes with this formula, and you'll see that it's just what we just did. I'm just going to keep things. We had a very specific problem we were working on last time with the road trip story, a very specific function we were plugging into, and this is just doing it in a very general way. So our function could look like anything. Let's just say we still had something very similar to the road trip story. Doesn't matter what the function looks like, but we're at a point x right here, and then we go some distance h away, makes this the point x plus h along the x-axis. And so that's again what we had here originally. We're going to take a change in our x values. So at this point x, I plug into the function to get my y value. So this would be the point x, f of x plus h. And again, no matter what our function was, we just had 5x squared plus 50, and we plugged in, or 5x squared plus 50x, and we plugged in 3, right? And you would do that no matter what your function is. So this is just saying that in very general terms. Take your x, plug it into whatever your f of x is, and that's how you get your y. So this is the general way of saying, at x, this is really a height of f of x, right? That's how tall you are. And then you move h away. Again, you're doing all this in letters. It seems very general, but just keep going back to the south of the border road trip. I go h away, and I go to a new point, another point on the function. So this would have to have the coordinates, x is x plus h, and then the height is just whatever happens when I plug x plus h into the function. So that would be f of x plus h. So those are the 2 points that we have on the function. Connect them with a line, and you then have a secant line. Right, and this one must have a height of f of x plus h. That secant line has 2 points on a function, so we can easily get its slope by taking our change in y, y2 minus y1, y2 minus y1, so there it is right there. That goes in the numerator. And then in the denominator, I put the change in x, x2 minus x1. X plus h minus x, which again we said really just simplifies to h. And so that means that this part of the formula in the box, that represents what? That represents the slope of a secant line. And then what happens with this? This part in the oval here, that's our limiting process, right? Without that, you're just getting a slope of the secant line. That was elements in the table, 70.5. Then you made h smaller, 70.05. So as h goes to 0, the slopes of your secant lines must converge to the slope of the tangent line. And this is exactly what we did with that table. This is exactly what Newton and Leibniz, the founders of calculus, did. They did anytime they wanted to get an instantaneous rate of change, they used this limit definition. No matter what the function was, crazy, e to the sine x plus x squared, whatever, no matter what the function was, they would apply this limit definition, and they could get an instantaneous rate of change at any point. So if you wanted the derivative at x equals 2, that was south of the border, right? And in the south of the border, in the road trip story, x equals 2 was the south of the border. So you'd plug in 2, and that's what we did in the table. That's what we did in a few slopes of secant lines. We had a slope of 75, 73, 71, and kept getting closer and closer to 70.5, 70.05, and got closer and closer to that slope of the tangent line that we wanted. Okay, so next thing to notice about this limit definition, exactly what it means. You want to make sure you understand completely the three pieces of this. Three pieces being what's in the box, what's in the oval, and what's over here in the box. Those three pieces represent exactly this, what's in English here. And the next thing we want to make sure we understand about this limit definition of the derivative is that it itself, if you were to apply this to a particular function for any x, rather than at x equals 2, you can do it for any x, you create something called the derivative function. So I'll make a little space here. Okay, the derivative is itself a function, so what do I mean by that? Let's go back to maybe working an example. So you'll see this kind of problem often this semester. Find f prime of x, which is saying find the derivative at any x, which is another way of saying find the derivative function for the original function, 5x squared plus 50x. Now for us, you know, this 5x squared plus 50x was attached to this story that we're taking a road trip. This was miles, distance traveled is your y, x was your time. But later in the semester, we're just gonna kind of crank away. I'll give you a function, tell me the derivative. I'll give you a function, tell me the derivative. I'll give you a function, tell me the derivative. You need really good at doing that throughout the semester, particularly in chapter 2. And so we want to make sure we understand what we mean when we say f prime of x, that it is itself a function, and how that's different than the original function. So remember our picture for the original function, we had x comes in, you follow the function rule, whatever it is, and it spits out a y, right? So an x comes in and it spits out a height on the graph. Another x comes in, it spits out a different x, and so on. And it makes, once you connect enough of those points, you can plot points and create the function. We're going to have a different box for the derivative. And x will come into the derivative function. And we're going to do some work, but we'll eventually see that f prime of x for this one, it's going to take us a good bit of work, is 10 plus 50, 10x plus 50. So if x was 2, I put in 2 for x, multiplied by 10, 20 plus 50 is 70. So it's 70 miles per hour in the road trip story. When we were at x equals 2, you've traveled 2 hours, you're at south of the border. What is your instantaneous speed? You'd say 70. Again, we saw that from the table, we saw it from the limit definition, trying to make our secant lines converge to the tangent line. But here's a formula that says you give me an x, I'll spit out a derivative, and that derivative is a slope of a tangent line. So what comes out here is a slope of a tangent line. Whereas here, what comes out, a y at some x, what it spits out is this. This distance here is a height. Over here, same graph, same point, what it spits out is a slope of the tangent line, an instantaneous rate of change. For our south of the border road trip story, it is an instantaneous speed. Okay, so you could see if you wanted to know what is the instantaneous speed after you've only been traveling 1 hour, you plug that in. 1 hour, 10, 60 miles an hour. After 1 hour, your instantaneous speed, radar gun speed, after 1 hour, 60 miles an hour. Suppose you want to try it at 3 hours. 3 hours, you're going 80 miles an hour exactly at 3 hours. You could try it at hour 1.1, right? And you just plug in 1.1 times 10, 11, 61 miles an hour. At time hour 1.1, you're going exactly 61 miles an hour. So again, a function itself. You give me an x and I'll spit out a rate of change, an instantaneous rate of change. Okay, so I just pulled this one out of the air, right? I didn't show you how I knew that I could look at this function and get this derivative. Again, in chapter 2, you're gonna get really good. This is actually a rather easy one. You'll be able to look at this function and go from here straight to here. For now, you have to watch me do a limit definition at least once. I'm not gonna make you do them, I just want you to watch so you understand and appreciate all the shortcut rules that you're gonna learn that enable you to go from here to here rather quickly in chapter 2. Okay, so watch. Last part of this lesson is we're gonna do the limit definition for that function. So I need some space. Again, the example is find f prime of x for, and I'll give you a function. You can do this repeatedly in this class. And we have to do it, the only way we know at this point is with the limit definition. So I need to figure out what this is. The limit definition is written right above. It's something you want to memorize because we're going to use it in our quizzes and our exams. Or better to memorize, understand. And then you don't even, there's nothing to memorize, you totally get it. Like, oh, that's right, the derivative actually is derived by taking slopes of secant lines. Okay, those happen at 2 points, a general point x and a point x plus h. And so I'm going to take the difference in the y values divided by the difference in the x values. So I'm going to start from that general definition, and then I'm going to apply the specifics for my specific f. So really easy stuff you can start off with. Limit as h goes to 0. The denominator stays the same. Nothing I can do with that yet. Then I'm going to put something in parentheses here. That'll be f of x plus h, but I'm going to do a little work to figure out what that is. F of x, you just copy as it's given. 5x squared minus 50, or say plus 50x. And then again, what goes in this empty box here, we're going to do a little work on the side. We're going to figure out what, if f of x is 5x squared plus 50x, I want to know what f of x plus h is. Well, that's 5 times x plus h squared plus 50 times x plus h. So now I need to do some FOILing, x plus h times x plus h, and then multiply that by 5. So I'll write it all out. This will be distribute the 50, we'll get 50 x's plus 50 h's. And then here I'm going to FOIL this first, outer, inner, last. So x squared times 5 on the x squared plus the inners, there's an xh and another xh, makes 2 xh's, plus the last is an h squared. And then still copy along the 50x plus the 50h's. And now we're almost ready. This is 5x squared. I'll just distribute the 5 to those 3 places, plus 10xh plus 5h squared. Lots of algebra, right? And we're still just prepping for this. All of that represents f of x plus h. So that goes in this box right here. Is there anything we can combine? No, it doesn't look like it, so we got to squeeze this all in. 5x squared plus 10xh plus 5h squared plus 50x, make a little room, plus 50h. Minus f of x. Right, and this is also in your journals. You can follow along. This is the page called Calculating the f of x function. So you can follow the algebra and arithmetic here. All right, so at this point, I need to maybe hopefully some things cancel out. And if you're doing a limit definition problem thing correctly, a few things should always cancel out. So I see that I have a positive 5x squared and a negative 5x squared, a positive 50x and a negative 50x. And so the numerator just becomes these 3 remaining terms, 10xh plus 5h squared plus 50h, all divided by h. Again, in these limit definition problems, you might have had to do some of these what are called difference quotients in pre-calculus class, and you see that there's an h in each one of these. So I could actually factor an h out of the numerator, and I'll have, this is the limit as h goes to 0. I haven't done that process yet, so I just keep writing it and carrying it along. I'm going to take an h out of the numerator, so I'll be left with a 10x plus a 5h plus a 50, all divided by h. And now I see that at this point I can cancel these h's. H divided by h gives me 1. And so now I have the limit as h goes to 0 of what's left is just 10x plus 5h plus 50. There's no more fraction, and that's good. That's the whole point of doing these two, is to get rid of the fractions so that you can then evaluate the limit. All right, so now we're ready. We've simplified this quite a bit, and we're ready to see what happens when h gets closer and closer to 0. When h gets closer and closer to 0, what happens to 10x? It's still just 10x. It doesn't have any h's in it. It's not affected by h. Same thing with the 50. When h gets closer and closer to 0, 50 is still just 50. The middle term is the one that is affected. What happens when h gets closer and closer to 0? 5 times h also gets closer and closer to 0, right? And in fact, as h gets so close to 0, but doesn't touch it, this thing goes away, right? So you can actually think about this is like going to 0, and that means what you're left with is just 10x plus 50. So that is the derivative. That's what we had. I had just pulled it out of the air and said, okay, the derivative is itself a function. You give me an x, I throw it into this function rule here. When x is 2, I multiply it by 10 and get 20, add 50, 70. And so that tells you that for this function, when x is 2, the slope of that tangent line at x equals 2 is exactly 70. In our road trip story, because that's what this represented, that was a rate of change. It was 70 miles per hour at exactly x equal 2, at exactly south of the border. Okay, again, understand the limit definition. I'm not going to make you calculate it, but I want you to understand quite a bit of algebra, but really all you're doing is taking slopes of secant lines and making those secant lines converge to the tangent line where you get a slope of a tangent line. A derivative represents the slope of a tangent line. A derivative is an instantaneous rate of change. Those mean the exact same thing. And the only way we could originally do it until we get to chapter 2 is through this, the historical definition that Newton and Leibniz came up with for how to compute an instantaneous rate of change using the limit definition. Oh yeah, and then last piece, make sure you understand that the derivative is itself a function. The original function, you give it an x and it spits out a height on a graph, whereas the derivative function, you give it an x and it spits out the slope of a tangent line. It does how steep your function is there. All right, that's it for that topic. Thank you.